So in this video, we're going to discuss the concept of capacitance and capacitors. A capacitor is simply any material that stores electric charge by separating charges over some distance, usually denoted by the letter D. A parallel plate capacitors are two parallel plates with the associated surface area that is separated by that same distance, right? That I noted earlier to D. Right. So two plates are usually made of conductive material. That's what allows charges to freely accumulate and flow towards them. The separation of charges creates an electric field, right? The direction of which points from positive charge to negative charge, right? The field lines indicate the theoretical direction that the positive charge, or indicates the direction that the theoretical positive charge would move, would move in. And so usually also within a circuit, we have a voltage difference established. Usually it's accomplished by inserting a battery within the system. And so the voltage difference allows for a non-neutral sort of differential between both plates and enables for the electrons to move from an area of low voltage to an area of high voltage along a permissible path. So now if we wanted to look at sort of the total amount of electric charge that can be stored on a given capacitor plate, we would find out that that is directly proportional to the voltage difference, right? And so that's how we essentially get the equation Q is equal to CV. Right? Q is equal to CV, right? The proportionality constant C is known as our capacitance. And there's a linear relationship between Q and V, right? Whereby the slope of the line, the slope of that line is equal to the capacitance of the system, right? This means that the steeper the slope is, right, the greater the value of the capacitance, the more charge can be stored by the plates per unit voltage. Mathematically, this essentially means that C is equal to Q over V, right? And so already we see that rise over run, right? That slope that I was talking about, Q, the total amount of charge being the rise, and then the voltage of the circuit being the run, and that is the value of our slope. Since this is the case, right, what are some of the determinants of capacitance, right? That'd be really important to know. And so there are four main determinants for capacitance. One of them is the size and shape of the capacitor. Second is the surface area. Surface area is a relationship that is directly proportional, right? The greater the surface area of the capacitor plates, the greater the capacitance. Third, we have the separating distance, right? This represents an inverse proportionality relationship. The greater the separating distance between both plates, the smaller the capacitance is. And lastly, we have any substance that's found between the two plates, right? This is termed a dielectric, and so we'll touch more on that later on. It's important to note that the capacitance does not depend on the voltage difference nor the electric charge. And so the greater capacitance, if we want to store greater capacitance, if we want to have a greater capacitance, how can we accomplish that? We can do that by having a greater amount of charge for the same voltage, a greater surface area, or decreasing the distance between the plates. And so the value of capacitance, this equation here, is actually what shows us this relationship dependent on surface area and distance, right? We see kappa epsilon naught A over D, right? Capacitance is directly proportional to surface area. So if surface area increases, right, because it's a numerator, our capacitance will also get bigger. If the diameter, if the separating distance, increases, right, because we're then divided by a bigger number, the capacitance will decrease, right? Inverse relationship with relation to the separating distance, and a direct relationship with relation to the surface area. Okay, So next we can talk about how do we find out what the energy stored within a capacitor is, right? How do we get the magnitude of that energy? And so essentially what we can do is we can realize that the potential energy stored within the capacitor is equal to 1/2, well, we'll do Q squared first, and then the 1/2 is where this 2 comes from, and then times the capacitance, right? And so because we know that Q is equal to CV, let's say we don't know what the value of Q is, for example, right? We're not given that in the problem. Well, we know that Q is equal to CV, so we can just input that into our equation. And so this, we get CV squared over 2 times C, right? This equals C squared times V squared, which is equal to 2 times C. We have 1 C up here, and so that simplifies to C V squared over 2. And so that's how you get this equation here, 1/2 times C times the change in V, right? So V is understood conventionally to mean that it is the voltage difference, right? You can't just have, sort of one voltage. It's always a voltage differential, right? One area in space is voltage rich and the other is voltage dependent, and the movement of charge is across a voltage difference that's established, right? So the battery here has a voltage difference. It has a positive end and a negative end. It establishes a voltage within the system, but that really is the difference between the voltage at this point at the negative end and the voltage at the positive end. So, and we know that this is a low voltage point, the minus end, and the positive end is a high voltage point. Okay, and so there's a nice little mnemonic here to help with that, and to help remember the equation. And so if, for example, we're not given the capacitance, right? In this first instance, we weren't given the charge. So let's say we're not given what the value of C is in the problem. Well, all we have to do is rearrange our equation, right? We know that if we know that C is also equal to Q over V, right? So we can rewrite this equation to be, 1/2, I'll separate everything out. It's 1/2 times Q squared times 1 over C. And so we can rewrite this as, well, that's just 1/2 times Q squared times 1 over Q over V, which is really 1/2 times Q squared times V over Q, right? And then cross out a Q, we get 1/2 Q times V, right? So that's how you get the second equation right here. Okay, awesome. Okay. So next, we can talk about capacitors in series. And so very quickly, what ends up happening is charges cannot cross this area of space here, right? This is a space, and we know that that's a magnitude D. So we can call that D1, D2, and D3, right? Charges can't cross that. They can only pass through the wires, essentially, you can think of it. And so what actually ends up happening is that when we have our minus and our plus end here, is when electrons are here and we introduce this voltage difference, electrons will move this way, right? They're trying to get to the positive end, right? Because this, again, remember, is high voltage. And so the electrons will move here and they'll accumulate on this left side of the capacitor plate 1. what that will do is the electrostatic repulsion of all of these electrons just bouncing around on each other will push the electrons that are on this side of the plate, and it will cause them to move here and accumulate on the left side of the capacitor 2 plate. And that will reverberate, right? The electrons that are located on the right side will be pushed and moved to accumulate on the left side of capacitor plate 3. And then lastly, the electrons that are free over here essentially are the ones that will move towards that positive plate. Right. And so these electrons that are here are not the same ones that end up on the right side here, right? These electrons are not the same as these ones, right? Because these electrons have no way of passing through this barrier that I outlined here, or this space, if you will, the separating distance. So that is how the electrons move around the circuit, right? Just so people understanding that electrons are not crossing the separation between the plates. Right? They're forced to push electrons that are on the other side, and those are the electrons that end up moving. And so when the capacitors are in series, right, we know that they're in series because they're next to each other. What ends up happening is, so we know that we're trying to find out what the equivalent capacitance is, right? So you have these 3 capacitors here, right? What is the equivalent capacitor that we need to be able to hold the same amount of charge at the same voltage? We want to find the single equivalent capacitor that will hold the same quantity of charge under the same voltage difference. So how do we do that? We know that when the capacitors are in series, right, the total voltage here, V, established by the battery, is not the same voltage that each capacitor is experiencing, right? Because the electrons are essentially forced to push their neighboring electrons, right, that voltage is slightly different across the 3 capacitors. And so what does that end up looking like mathematically? What that means is that the total voltage, right, the same voltage that's established by the battery, is actually going to be the sum of all the individual voltages. So V1 plus V2 plus V3. And so the total voltage for the capacitors placed in series is equal to the sum of the individual, or the total voltage for capacitors placed in series is equal to the sum of the individual voltages. So now, because Q equals CV, right, or rather, which is essentially the same thing as V is equal to Q over C, we can rewrite this as, V Q over C here, and we'll call the C equivalent, is equal to Q over C1, the capacitance associated with the first capacitor, Q over C2, the capacitance associated with the second capacitor, and then Q over C3, right? Again, the capacitor associated with the capacitance associated with the third capacitor. So what does that simplify to, right? That simplifies to, because Q, the total charge, is the same, Q can be factored out. And so what we end up with is essentially 1 over C1 plus 1 over C2 plus 1 over C3, right? That's how we got this right end, right? And essentially then, in order to get, because we can factor out Q out of the entire equation, we can get Q here, 1 over CEQ is equal to Q, right? But then you can see that if it's gonna be Q times, you can divide this Q by that Q and you'll get 1, right? So you can just take it out of the equation. And what we're left with is just 1 over C1 plus 1 over C2 plus 1 over C3. And you can even take out these parentheses because now the Q is gone. And so that's exactly how we derive this equation up here, right? The equivalent capacitance that you will need, right? The single capacitor that you will need to replace 3 capacitors in series will be the reciprocal of each of the capacitances of all those 3 capacitors. Okay, so now what does that look like for capacitors in parallel? For capacitors in parallel, you can tell they're in parallel because they're sort of lined up pretty nicely, right, in a parallel fashion, right? So that's a pretty simple way of analyzing that. And then now let's look at this a little bit more specifically, right? In our system, remember that the voltage is being established by our battery here, right? Negative end being the low voltage, positive end being the high voltage. What happens here now is when an electric charge, right? We'll just say this, right? When an electric charge is traveling, right? Remember, they are traveling to the positive end. So it will travel in net, right? The electrons will travel this way. Just the identity of the electrons that end up on the right side will not be the same as the electrons that started because they can't cross the gap. And so what will end up happening is when the electric charge reaches a branch point, it will split. And so some of the electrons will end up accumulating on capacitor plate 1, some will continue. Some will end up accumulating on capacitor plate 2, and again, some will continue. And some will end up accumulating on capacitor plate 3. In this way, right, we have essentially a split of charge across our capacitor system. So what does that mean for us mathematically? So again, we're trying to find the equivalent capacitor that will replace all 3 capacitors, but now will replace all 3 capacitors that are located in parallel. And so some of the charge, like I said earlier, will collect on C1, some of the charge will collect on C2, and some of the charge will collect on capacitor 3, right? And we're trying to find the equivalent capacitor that will replace all 3 of these capacitors for the same, that will store the same amount of charge at the same given voltage, right? If we wanted to know what that total charge was, we could add, right? We could simply add each of the charges that are located on each capacitor, right? The charge located on capacitor 1 is Q1. The total charge capacitor located on capacitor 2 is Q2. And the charge located on capacitor 3 is Q3. Well, because they all split, the total charge essentially was coming from the battery. So the Q total, right, the total amount of charge that's present in the system is equal to the sum of Q1 plus Q2 plus Q3. And because Q is equal to CV, we can rewrite this as CV, right? All of this is total. Actually, I don't need to specify that. So CV, the total charge, will be equal to the charge on capacitor 1 plus the charge, plus the charge on capacitor 2 plus the charge on capacitor 3, right? But now, I said earlier that the total voltage is the same for capacitors in parallel. So I can factor out a V here and just have the equivalent capacitance is then equal to V, because V is equal to V1 is equal to V2 is equal to V3, I can put all of that as V, right? Because they're all equal to each other, right? Then that means that this is then gets simplified to C1 plus C2 plus C3. And so because I have V on both sides of the equations, I can divide that, cancel that out, factor it out. We get the equation that we see up here. The equivalent capacitor is the sum of the capacitances of the capacitors, right? So what does this tell us? What do we notice right mathematically, right? We notice that by connecting capacitors in parallel, we can increase the total effective capacitance, right? The effective capacitance here is the sum of the capacitance of all three of these when they're in parallel, as opposed to here being the sum of the reciprocal, right? So you're essentially adding a smaller value when they're in series than you are when they are in parallel. So if we increase, right, so by connecting capacitors in parallel, we can increase the total equivalent or effective capacitance, and therefore we can hold more charge, right? Remember, Q is equal to CV. Q is directly proportional to the capacitance. So if the equivalent or effective capacitance is greater, i.e. it increases, then the total amount of charge we can store also increases. So lastly, we can talk about the dielectric. A dielectric is essentially a non-conducting material that's inserted between any two capacitor plates. And so I can draw capacitor plates as straight lines like so, and I will denote the dielectric as a yellow here. Usually, you can think of it as it's a non-conducting material, and so a very good one is fat. Fat is a very non-conducting material that's often used, or some derivatives of that, and so it's very hard because of their associated non-polarity for charges to easily influence the movement of those electrons within the molecules. And so what ends up happening is the dielectric layer will influence the effectiveness with which electrons, or the accumulation of charges on this side of the capacitor, will influence electrons to move on this side, right? Because that's essentially what's happening. They can't cross this gap, right? This is the separating distance, D. They can't cross this gap. And sometimes the dielectric allows for the movement of electrons, but then that will depend on the dielectric constant, right? And so what we see is we can look at the relationships, right? How does the dielectric impact the capacitance, and how does it impact the voltage, right? And so we're told from these equations that the voltage is equal to V naught time divided by K. V naught represents the voltage in the absence of the dielectric. And so the new voltage then, if there is a dielectric presence, this equation tells us that by adding a dielectric layer, depending on what the magnitude of that is, there's an inverse relationship, right? And so if we increase the dielectric constant, this is telling us that the total voltage will decrease. And similarly, or antagonistically, if we decrease, right, I'll use a different color so that that's more visualized. If we decrease the dielectric constant, then we increase the voltage across the capacitor plates, right? And so now we can look at the relationship between the capacitance, right? How is the capacitance impacted by the presence of a dielectric? Well, this is directly proportional, right? If we increase, and again, the capacitance C naught here is the capacitance, right? C naught here represents the capacitance in the absence of a dielectric. right? And so what this is telling us is if we increase the dielectric constant, and again, sorry, the dielectric constant is what K is, right? K equals the dielectric constant. So if we increase the value of K, we will increase the capacitance. If we decrease the value of K, we will decrease the capacitance, right? This is a direct relationship, and this is an indirect relationship. Okay.